Alright, welcome to Solubility Easy World Science Channel. In this video, I'll be handling solubility products. Remember to watch my previous video on solubility general. Towards the end, I introduced this subtopic of solubility known as solubility products, or KSP. Sometimes students might find the calculation difficult, but I promise you one thing, I'm going to simplify it just like I did in the solubility itself. But for you to understand this topic very well, you need to have the good idea of solubility in general before we talk about the solubility product. Please don't forget to subscribe and share this video. Expand the science community. Much love from me to you. Now, the topic is solubility product brackets KSP. And this K here means that it's a constant. Actually, when I use the word solubility product, I am trying to express something when a solid is in equilibrium with its ions in aqueous solution. We can now talk about solubility product. It is applied in determining when precipitation will occur, and it is more effective for what? For salts that are sparingly soluble in water. It does not work effectively well for extremely soluble salts. You get what I'm saying? And remember, product is the answer we get after multiplication. So solubility product is going to get the multiplication of the concentration of the individual ions that makes up a particular solute in water. So solubility product KSP is just an equilibrium constant, which is derived when a solute is in equilibrium with its ion. When a solid that dissolves in water but sparingly in water is in equilibrium with its ion, which means we must attain saturated solution. Saturated solution. And in a saturated solution, there must be undissolved solute. So when there is an equilibrium established between the undissolved solutes and together with the ions in aqueous solution, we talk about KSP. So this is a kind of an equilibrium constant, which when we apply, if there is a solid A plus B, this, or we just take it as only AB, which is solid, it doesn't dissolve. If you put it in water, it will dissociate to give you A ion, which might be A plus B minus. In this case, after balancing the equation, we will have some coefficients like X, Y. Even this one might have its own coefficient after balancing the equation. But because of the fact that this is aqueous, this is the ion, so we are going to multiply the products of the concentration, the molarity of this, times the molarity of this, raised to power the coefficients of each one gives us the solubility product. Which means, to establish equilibrium, we show that the reversible reaction must occur, like I told you in the beginning, when a solid is in equilibrium with its ions. These are the ions formed from this solid. Bringing a known salt, silver chloride, is sparingly soluble in water. It doesn't dissolve all well. Some might tell you it is insoluble, of course, but small part of it dissolves in water. If this dissociates, it will give us silver ion plus chloride ion. So the solubility product or solubility product is applied here is equal to the dissolve, such that the rate of the solution is equal to the rate of the one being precipitated. So we have S. So the solubility of this undissolved is 1, because it is not the concentration, of the undissolved is automatically going to give us 1 because it is 100% undissolved. Remember equilibrium constant, how to derive it. This will give us way to understanding solubility products and its calculation. So how do we derive equilibrium constant? We have that in equilibrium constant, we are going to use the, over here are the products. You take the products, let me just, you're putting X, Y, because it's balanced already. This is 1 and this is 1. Everything is balanced well. But in equilibrium constant, what do I have here? The KSP here automatically becomes, take that of the product and divide by the reactant. Take whatever that is on this right hand side and divide by what is on the left hand side. And by doing this, what do we have? This is Ag plus raised to power what is here. And what is here? What is here is 1. So raised to power 1, which remains the same. Because we are talking about products, we say now multiply by the next ion raised to power the coefficient, which is also 1. In this case, at equilibrium, we will have that Ag and AgCl will be also what? We say divided by the same thing. This is our product, this is our reactant. So our KSP will now be equal to this over this, will now be AgCl all raised to power 1. But because of the fact that, how do we now know this? We are going to bring in the law of mass action. That's the molarities of this is determined. The concentration of the undissolved is 100%. Do you know why it's 100%? Because it's just pure salt. Like if you bring solid sodium chloride, the concentration of that sodium chloride you are having is 100% because there is nothing there again. But it's when you now add it to water, we now have percent contributed by water and the percent contributed by the salt itself. But here it doesn't dissolve, which means we can take this as 1. So invariably KSP, which will now be what? You take the ions, multiply them, and divide by 1. So this should be the solubility product of this reaction, because of the fact that the solubility of the concentration of the undissolved is taken as 1 because it's almost 100% uncertain. So this is the KSP of this reaction. Bringing it to real life, another equation that we can have, if we have calcium fluoride, if you are to dissociate this is solid. If you dissolve it in water, it will give you calcium ion, that's Ca2 plus 2F minus. In this case, you find out that we have now that coefficient here varies. It becomes 1:1:2. If you are to derive the equilibrium constant, what are we taught in about equilibrium constant? It will be, this solution will be saturated in the presence of undissolved when the rate, the number of moles dissolving is equal to the number of moles being precipitated, such that forward and backward is happening at the same rate. Taking the constant, what do we have now? The KSP will now be Ca what? 2 plus raised to power, what's the coefficient? 1. Multiply, because we said product, multiply by 2F fluoride ion, also raised to power 2. You raise it to the same coefficient. Remember this thing, I'm saying multiply because we move from here to here. This implies that 1 mole of CaF2 will give us 1 mole of calcium ion and 2 moles of fluoride ion. And the coefficient is T2. So these two here repeating is telling you to multiply the number of the concentration of this by 2 and raise it by the power of 2. This is all we know about deriving equilibrium constant. So by doing this, we have gotten our what? KSP. And this means solubility in mole per dm cube, solubility in mole per dm cube. That is the meaning of this calcium ion, the solubility of it in mole per dm cube, the solubility of fluoride ion in mole per dm cube times 2 and raised to power 2. We have established the solubility product of this particular compound. So bringing it to action, what if we have some compounds that have more multiple ions? Let's go. If we have calcium tetraoxophosphate 5, dissociate this, forward, backward, we will have Ca32 minus, 2 plus, calcium ion, but we have 3 atoms. You have to put that 3 to balance it. Then plus what? 2, because this is 2, PO4 3 minus, of course. This is the dissociation. What is the solubility product? Is multiply the molarity of ions times this by 3, molarity of this times 2, and raise it to power their coefficient. Nothing concerned with this charge. This is charge. This is plus 2. This is minus 3. Remember that atoms will balance and the charges will balance also. The total charge here is what? 0. That is solid. But the total charge here is 3 times 2 is plus 6. 2 times minus 3 is minus 6. Plus 6 minus 6 is equal to 0. So charges are equal. 0 here, 0 here. So while writing this, make sure that both atoms and charges do what? Balance. Alright? So what's our KSP from what I taught you? Simply pick this. KSP is equal to, pick the first ion, calcium ion, raised to power what? I omitted that this is not calcium. We are going to write the 3Ca, please. The 3Ca2 plus raised to power the same 3. Multiply, because we said product, by 2PO4 raised to power 3 minus, still you raise it to the coefficient square. So this is it. And remember I told you that what is this thing representing is solubility in mole per dm cube, solubility in mole per dm cube, which is determined by this. This implies that when 1 mole of calcium tetraoxophosphate 5 dissolves in water, it will dissociate into 2 ions. 1 mole of calcium tetraoxophosphate 5 will give us 3 moles of calcium ions, which means if the molarity of this is 2, it automatically tells us that it's going to give us 6 moles of calcium ion because of what? What is here is 1. This means 1 mole. This is just 1 mole. And when it dissociates, it gives us 3 moles of calcium ion. So 1 mole of this will give us 3 moles of calcium ion and 2 moles of phosphate 5 ion. This means that if this is 2 moles, it will give us how many moles of calcium? 6 moles. Why? 1 gave me 3. 2 will give me 6 in that order. So what determines the value of this calcium ion and phosphate 5 ion depends on the molarity of the salt itself that you are dissolving in water. Alright, having explained this, I guess we start solving. We're going to face a situation whereby if you are given solubility product, you will determine solubility in mole per dm cube. Then if you are given solubility in mole per dm cube, you will determine solubility product. Like I said earlier, this will help us to know when precipitation will occur, or when a reaction, when a solution is unsaturated and when a solution is what? Saturated. If you exceed the solubility product already established, there is a table where solubility product for spirally soluble compounds are established. We call it solubility table, and it uses what? Room temperature. Room temperature is what we use to establish them. Remember, this doesn't work well for highly soluble salts. Though your exam body might ask you questions using the highly soluble salt, but the practical aspect is we use spirally soluble salts to do this KSP. So to know the maximum solute a given solvent can take, to know the dissolving capacity in a given volume of what? Solvent at a particular temperature. So if you come to that solubility product, lest I forget, what's the unit for solubility product? Solubility is in mole per dm cube this way. Okay, we move to solving examples. I'm going to set the first example. Example 1, you might handle up to 3 or 2 examples. If the solubility of lithium tetraoxophosphate 5 is, if the solubility of lithium phosphate, lithium tetraoxophosphate 5 is 9.68 times 10 raised to power minus 4 mole per dm cube. Calculate the solubility product. Calculate the solubility product. The solubility product is marked KSP. Remember, this figure is not practically obtained. I just quoted a number to help us solve, okay? Solution. What we are going to do here first is find out the figure and write the formula of the compound, lithium tetraoxophosphate 6. This should be Li3PO4. This should be the correct thing. Tetraoxophosphate 5, sorry, lithium tetraoxophosphate 5. This is the formula. Write the formula well if it is not written. Then the next, you dissociate the compound into its ions, which will now be, when you dissolve it in water, it will spirally dissolve to liberate what? Lithium ion. Lithium is among the group 1 elements, and all the group 1 elements have that +1 as charge. But because there are 3 atoms, I'll put 3 here, plus PO4 as a group. How do you know the charge present? I said phosphate 5, tetraoxophosphate 5. That means this phosphorus here is 5. I'm teaching you how to know the charge that will be on top of this as a group. This means that P is 5. Oxygen is -2, and -2 times 4 is -8. The oxidation state or the combining power of oxygen atom in in most compounds except in peroxide is -2. So over here is not an exception. When you look at this, you say -2 times 4, it will be -8. So 5 minus 8 is equal to -3. That's why we put 3 minus. That's the net charge. Can you guess the net charge on OH? Oxygen is -2, I've said it. Hydrogen is +1, just like the alkali earth metal. So -2 plus 1 equal to -1. Therefore, the charge here is minus. So this is how to put charges on grouped atoms. So let's move on. Remember, we have this settled already. Atoms are balanced and the charges are also balanced. 3 times 1 is 3. 1 times -3 is -3. So 3 minus 3 is still 0. Having seen this, we have established the number of ions involved, which means Ksp now is equal to what? 3Li plus raised to power, that's 3, multiply by what? PO4 3 minus raised to power 1. So with this, we are going to represent each molarity. Remember that they have told us that the solubility of lithium in mole per dm cube is this, that we should calculate the solubility product. That means that from this we balanced it. It shows that, permit me to bring this down, this implies that 1 mole of lithium phosphate will dissociate to give 3 moles of lithium ion plus 1 mole of PO4 3 minus. So the product of this whole ion, and they gave us solubility. This also implies that our solubility here is S. Alright, looking at this means that 1 mole of lithium tetraoxophosphate 5 gives us 3 moles of lithium ion and then 1 mole of phosphate 5 ion. Then we defined earlier that it is the molarity of the ions raised to power their coefficients and multiply the whole thing together. So we are going to represent solubility with S. This is our S. Is that clear? So that means this S, which stands for solubility, because of this, will give us 3S. Of course, I'm now replacing every ion here with S because it implies that 1 mole, like I said, of this will give you 3 moles of this. So whatever S, 1 S will give us 3 moles of S of lithium, and then also plus what? And also 1 mole of what? S. So the total S we have here is 3S and 1S for phosphate ion because 1 is here. That means we now derive our Ksp like we did here. The Ksp automatically implies that it's going to be now what? 3S raised to power the coefficient, which is 3, multiplied by S again raised to power the coefficient, which is 1. So we already know what our S is, which is the solubility. So we can now fix in values and get our answer. That means our Ksp will now be equal to 3 times 9 3 times all right. So our Ksp, we are going to multiply this out 3 times 9.68 times 10 raised to power minus 4, all raised to power 3 again because of this. Then multiply by 9.68 times 10 raised to power minus 4, still all raised to power 1, which remains itself. So from the calculator I have here, 2.904 times 10 raised to power minus 1, 2, 3 minus 3, 1, 2, 3, yeah. Then multiply it out, you raise it to power 3 again, multiply by 9.68 times 10 raised to power minus 4. That gives us our Ksp. If I raise this to power 3, my answer here will be, maybe I shift the camera, I continue here. My answer here when I raise to power 3 is 2.449 times 10 raised to power minus 8. Then multiply out by 9.68 times 10 raised to power minus 4. Automatically, we are looking at minus 11 at the end, because if you sum this is giving us 2. The total solubility product, our KSP now, is 2.37 times 10 raised to power minus what? 11 moles square. Remember I said it in the beginning, and what? dm6 is our final answer. If the solubility of this compound is found to be this, which is S, the solubility product is this. Now, in the reverse, the second example I want to give us is that, you understand my solving, I want to give us that this is the solubility product. Let us now calculate the solubility of this salt when the question gives us solubility product. So our next example is to help reverse this, to check if we can get this answer finally from this solubility product. That's our example 2. This is our example 2. To study this, I want to solve back. We have to start with the solution. When looking at this, we are going to apply the whole mathematical knowledge we have without skipping any. Solution is that we still need to go back to the KSP. We need to dissociate that same compound. We start there again. Lithium tetraoxophosphate 5. We dissociate to give us 3 lithium ion and 1 mole of tetraoxophosphate 5 ion, in that order. And for them to establish equilibrium, the rate at which is being dissolving in water will be equal to the rate at which something is displaced out. So to explain this solubility product, this means that if you exceed, if I should dissolve this amount of lithium phosphate that will exceed this solubility product, it means there will be precipitation coming out already. So now let us solve back. Looking at this, we also establish our KSP. Remember that this is our S, so that here will be what? 3S, and here will be just what? S. But if there is 2 here, we will say 2S. Simple. Use the S for representing the ions in charge. Alright? So in this case, we have now that KSP will now be 3S raised to power the coefficient 3 multiplied by S raised to power 1. Mathematically, time to expand this. So what does this imply? If you expand this square, it's going to be 3 squared. 3 squared, our KSP will now be 3 squared is 27, if my mathematics is correct. Is that right? 27S cube, not 3 squared, please. Cube 3 raised to power 3, not 3 squared, because 3 squared should be 9. I'm saying another thing, I'm doing another thing. So 3 raised to power 3 is 27, please. Then S raised to power 3 is S3 times S1. As usual, still apply your indices. Multiplication, this is S, they all have it in common. So this implies that our KSP now is equal to what? 27S3 plus 1, which will end up giving us 27S what? S4. And the job is done. They have given us KSP in the question. So we just place this KSP here and do the rest substitution. So having done that, our KSP was 2.37 times 10 raised to power minus 11 mole square equals 27S raised to power 4. At least we are looking for solubility. They said we should calculate the solubility, which is S. So we make S the subject of the formula by dividing with the coefficient by 27 divided by what? 27. So we are left with S raised to power 4 is equal to 2.37 times 10 raised to power minus 11 divided by 27. Now, mathematically, we will take this raised to power 1 over 4 to remove this 4. We will now have our x left alone. So to continue this math, let me get the answer to that one first. I think I'm free to clean here. So in this case, we will get, let me use my calculator and get the answer. Let me lift what we are solving here. S4 is equal to 2.37 times 10 raised to power minus 11 divided by 27. So I want to get the answer to this before removing this 40 to give us 8.777 continuation s raised to power 4. Fourth root of solubility. Fourth root of solubility is 8.78 on the approximation times 10 raised to power minus 13. Such that, having gotten this, our s will now be, to remove the fourth root, we have to raise this answer to the power of inverse of 4 times 10 raised to power minus 13, all raised to power 1 over 4. 1 over 4 should be 0.25. So my s is equal to 8.78 times 10 raised to power minus 13. Please, this is where error would have occurred. Serious one. All raised to power 0.25. That's the meaning. Okay? So I will press it separately. I've seen what I'm raising to power. Is giving us exactly where we started from. S is giving me 9.6799, and okay, you just continue times 10 raised to power 1, 2, 3, 4. Very correct. So mole per dm cube. Answer. See, we have gone back. Is exactly the same thing. If you approximate, it becomes 9.68. So it means that this method is working on how to calculate solubility product if you are given solubility in mole per dm cube, and how to calculate what? Your solubility if you are given solubility product. The third example should be, let me take another one. The next example will be, let's solve the example 3. I want to give you solubility product again for you to determine the solubility in mole per dm cube. I'm using real values now. I copied down the solubility of the compound, the solubility product, which is there. So example 3 says salt in water. To tempt you, they might say at 25 degrees. Yes, and this 25 completes the equation. It makes a lot of sense because temperature have effect on solubility, please. Okay, so like I told you, solubility products for standard is always obtained by dissolving the solute in the solvent at room temperature. Solution, I know you have already started trying yourself because this looks far easier than you expected. Simple. What did I say? Write out the formula. Thank God they have written it for us. I wrote it in the equation for you. Dissociate it, balance atoms and balance charges. Let's go. It will give us Ca2 plus. Remember, calcium is group 2 element and you have charge of plus 2. Just like magnesium. Then plus IO3. Even when you don't know, there will be 2 here in this place because of the 2 in brackets automatically. Even when you don't know the charge that will be on this. Iodate 5. This is 5 already. I called it 5 minus 6 is minus 1. So in this case, you see that the charge and the atom is balanced. We have total of plus 2 and total of 2 times minus 1. Please, this is not 21, this is I. 2 times minus 1 is minus 2. So charges is equal to 0 and also equal to 0 here. Now, what did I tell you? We are going to be representing solubility with what? S. And they have already given us our KSP already. So if this is S, one S dissociates to give us what? S plus what? 2S, 2 ions as a group. Now, our KSP this time around will now be equal to this S raised to power the coefficient, which is also 1, multiply. We are now converting plus to multiplication because we are talking about solubility product, right? Okay, times 2S raised to power the same coefficient, and applying this, automatically our KSP is equal to, expand this, S multiplied by what? 2 squared is 4. S raised to power 2 is 4S squared. So at the end, our KSP is 4 times 1 here is 4. S squared times 1S is S3. That's the mass there. If you are confused about it, you can simply say 4S2 plus 1, because this is raised to power 1. You add the 1 and the 2, which gives you 3. Now, they have given us KSP already, which is here. Time to replace the KSP with the value given to us. What will it be? 6.47 times 10 raised to power minus 6 is equal to 4S cubed. And we can find solubility, which is now to divide by the coefficients as usual, cancel, so that our S cube is equal to 6.47 times 10 raised to power minus 6 divided by 4 from the calculator department. So I can walk straight and tell you also that S alone is the cube root of 6.47 times 10 raised to power minus 6 divided by 4. You can carefully press this if your calculator will permit you and get your final answer. So you will have cube root of 1.617 or 1.618 times 10 raised to power minus 6. Okay, and the cube root is our answer. Solubility in mole per dm cube of the salt is now 1.23 times 10 raised to power minus 2 mole per dm cube. This is our final answer. All right. So with these few or 3 examples, I believe you can now tackle any problem concerning solubility product. I'm going to give you some work, maybe in a situation whereby we can have more than just raised to power 4, where we can have up to 5 as we have cube root, 4th root, 5th root. Maybe a question that can take you there. So try your ability by solving this. Calculate the only secret here is for exam purposes. If, let me use the one that gives us 2 ion. This one you might encounter this easily. Silver chloride is very easy to give you silver ion plus Cl minus. So if you are given solubility product here for you to calculate the solubility, just take the square root of whatever that is given to you, because at the end this is S, and S times S becomes S1 plus 1, because this is 1, will give us S squared. And to remove the KSP, which means your KSP, anytime KSP is equal to S squared, it implies that S alone is equal to square root of KSP. So if I give you for silver, you can encounter this because it's the easier one. If I give you the KSP of silver, for you to find the solubility, just take the square root of the KSP given to you. For instance, if I tell you that the KSP of this compound is 1.77 maybe times 10 raised to power minus maybe minus 8 mole square dm6, and I tell you find the solubility. Simple. The solubility is, because if you dissociate it, you get just S squared. Just press the square root of 1.77 times 10 to the power minus 8. You will get your what? Solubility in mole per dm cube. That is for those that gives only monovalent charged ions like silver chloride. So our class work will now be Okay, remember when you recover this by, it's insoluble, it's spirally soluble. If you recover it by filtration, you have to wash with water. While washing with water, some of them will dissolve away. So sometimes questions are constructed to ask you the mass lost. The mass lost is going to be determined by the solubility products and the volume of water used to wash it. Get that? So I don't prepare. If I prepare with that question, it will be very nice if I bring it here. But it's something you have to sit down and construct well. All right? Try these two classworks and let me see your answer in the comment section. Don't forget to subscribe and share this video. Much love from me to you. Stay majestic. Bye for now.